Hello, everyone. Welcome back to Jump On Air. We're so happy you've chosen to spend a bit of your Friday with us as we explore statistics, science, data, and of course, Jump. My name is Julian Paris. I am the Learning Strategy Manager here at Jump Software. And as always, I get the great privilege to be your host for Jump On Air. And it is a really great show we have for you today, this Friday. Today is all about predictive modeling. I'm going to show this schedule throughout the day to keep us on track. So you know if you ever have to disconnect, you can come back and catch your favorite segment. Remember, the link to remember is jump.com/jumponair. And that'll connect you right back to the live stream, no matter what device you want to connect on. After the show, we hope you'll visit us on the community at community.jump.com/jumponair. That's where you can interact with all of our show segments. You can watch on-demand episodes. You can ask questions. You can make show suggestions. You can interact with any of our guests and download any of the data or journals they use. Again, that's community.jump.com/jumponair. Now, just a couple quick announcements before we get started on the show today. Next week is another 2-episode week. We're off Monday for Memorial Day here in the United States, but we have a show on Wednesday and Friday. We have some great regular scheduled programs, and we hope you'll join us for those shows. Now, next Friday is actually an interesting day. It turns out that next Friday, we will have had 22 episodes of Jump On Air. It seems like just yesterday and also a lifetime ago that we were having our first episode on April 3rd. And 22 is actually a special number because I don't know if you know this. If we just go and Google how long is a season of television, it turns out that 22 episodes is an official full season of a show. This number has actually been changing quite a bit in recent times. 22 was originally the full length of a series back in especially the 80s and 90s. And a lot of that was having to do with how shows were broadcast on television. Now, most of us know that because shows are on things like Netflix or Hulu and dumped at one time, the number of episodes in a season actually has changed quite a bit. But 22 still has some significance. That is the official full length of a season. And when shows are purchased, that's often what they're purchased for. So, Jump On Air actually is going to end after our 22nd episode, but it's going to be just the end of season 1. Don't worry, you can't get rid of us that easily. What comes next, though, is a little bit of an open question. You know, will we have special summer episodes of Jump On Air? That's possible. Will we be renewed for a season 2 in the fall? Well, that's also possible. Will we get picked up for the big screen and come to a movie theater near you? That's probably not going to happen, but wouldn't that be fun to see us on the silver screen? No, Jump On Air is ending, but we do want to know what you want from us. And so after our show next Friday, we'll be sending out an email with a survey link to all of you who have joined us throughout these 22 episodes, because we want to hear from you what should be in store for us going forward. You know, we've loved putting on the show for you and bringing you statistics, science, and data talks throughout the last few months. And we definitely want to know what you want to see from us next. So I won't talk about this too much more now, but next week I'll make sure that you know that survey is coming to your inbox, and look for it Friday, right after the show ends next Friday, the 29th. So that's Jump On Air Season 1. All right. So we have a great show for you today, and I don't want to take any more time from our fabulous speakers who are here to present with us. We're going to kick today off actually with Mary and Pete, who are going to give us another tip of the day where they act out real life scenarios where a jump tip is the solution to a problem. Pete and Mary?
Hey, well, welcome to the Pete and Mary tip and trick of the day. Hey, Pete, how you doing?
Terrible. Thanks for asking.
Are you still you're the only one taking care of the kids today?
Yeah, my wife she's a healthcare worker, had to go into work today. So it's, this grizzled look is not for show. This is real.
Well, I'll tell you, I'm ready to swap houses. So if you want to come to Boston, and we can swap it out, but anyhow.
Yeah, I'll wait till the snow passes, but I'm in.
Yeah. Well, we're expecting some, so I guess I won't be fishing this weekend. Anyhow, I saw this Mastering Jump. It seems like it's every Friday. Jump offers these sessions, and who knew? But anyhow, I learned this interesting thing with the profiler. Do you have a profiler up or available real quick?
Let's see. Oh, wow. Look at that. I do.
Oh my goodness. We're psychic, Pete. If only we could make money.
I don't know how, but it sounds good.
So, so if you go up and maximize desirability, under the red triangle.
Yep.
Okay? Now, if you go up under the red triangle.
Uh-huh.
And slowly go down, because I'd always lose it, under factor settings.
Okay.
And remember settings.
Okay.
And call it max, the best, it rock,
Cool.
whatever. Now I want to look at screen size 4. So if you move over to screen size 4.
Got it.
And if we go up under the red triangle.
Uh-huh.
And we go down to factor settings.
Okay.
And put remember setting.
Okay.
And put setting 2 if you want.
Okay, that's fine, yeah.
Okay, so it's using 4, and so we get to save that setting, but there doesn't look like, well, there's a little bit of a difference, but not much. I must be doing something. Did I want to maximize it, or is there?
I think I see what you're trying to do here, Mary. So, so what you want is everything else to be able to change, but not screen size.
Yeah.
Okay, so to do that, there's a little trick in JMP. You can go under and do it from the red triangle, or you can hold down Alt, press in the factor that you don't want to change, and switch that to lock factor settings.
Oh, and then we can maximize desirability.
Yeah, and so now if we go there and we go maximize desirability, that meal time moved a little bit, but everything else stayed pretty much the same. So it allows you to do that, and you see that line is red now, so it can't change.
So then we can save this setting and say max for 4.
Yeah.
Oh, no, we want to go, remember setting, that's right.
Max or
4.
4, that's good, okay.
All right. And
yeah,
then,
look, it's a little bit different, just slightly, yeah.
Slightly. So if we want to do the same thing for 5?
Yeah, so if we
would do the same thing. We would unlock it, slide it over, now lock it.
Yep. We don't even have to unlock it. We can just click in here. It just can't move. Yeah, isn't that cool?
Oh, Pete, you're so smart.
And you're making my day, Mary. Oh, and you see when we maximize, now everything moves around. A lot changed there for 5. And we can remember settings.
Yeah.
There. Okay, got it.
Max for 5.
5. Okay, perfect.
Now, what the person did was, you have these settings for these different screen size, and you could have it be other variables, but they if you go up to File, and do Save As,
okay,
and if you save it as under that there as a interactive HTML,
okay,
and say Save,
okay,
this was cool.
All right.
Because if you had JMP Live, or if you had the interactive HTML, now I have the different settings remembered, and I can apply them, so I could talk about
it's
in
so
a meeting
cool.
that,
so
hey, if you look at it, isn't that neat?
That's really neat.
And I learned it all on a Friday afternoon.
Can't beat that.
Well, thanks, Pete. So we remembered settings, and we did the lock. And then we made it into an interactive HTML5 so I could share it with my team.
That's awesome. And I can look at this on a phone or a tablet.
Or integrate it into a dashboard and share it on live, whatever we want. Hey, sharing this information becomes a lot easier.
Yeah. And that's been your JMP On Air tip of the day. Thank you.
Thanks.
Thanks so much, Pete and Mary. Remember to interact with Pete and Mary at community.jmp.com/JMPOnAir. They would certainly like to hear from you and hear what other tips you'd like them to share. In our next segment, we have Elizabeth Clausen here. Senior Associate Research Statistician Developer, to take us through Machine Learning 101. Elizabeth, welcome to the show.
Thanks, Julian. Get the screen going there. All right. So, as Julian said, I am here to talk about Machine Learning 101. So, learning and jump, what is it? Do we do it? Well, of course we do, because this would be a very short talk otherwise. And a bonus, we always have. So, what is machine learning? I graduated with a PhD in statistics from the University of Nebraska, which is a very traditional statistics program, and we didn't really talk about machine learning. I'd heard of it because, of course, it's in the media and all of that. But when I started as a developer, they said, hey, we're going to have you work on some of these machine learning platforms. And I said, machine learning? What's that? And so I did what every enterprising researcher does. I went to Dr. Google, and it, of course, sent me to Wikipedia. And so it started out from Wikipedia. Machine learning is the study of computer algorithms that improve automatically through experience. And I said, what? I don't know. I'm not studying computer algorithms. I thought this was going to be, something that I use. Okay, Dr. Google, what's my next result? Encyclopedia Britannica. Machine learning in artificial intelligence, a subject within computer science, a discipline concerned with the implementation of computer software that can learn autonomously. A few more words, essentially kind of saying the same thing that left me going, okay, well, I'm going to be implementing computer software and it's going to learn autonomously. I'm not actually studying these algorithms. I'm going to be implementing them that other people have done. And so this led me to kind of my own mental definition of what I think of when I hear the word machine learning. So I say to myself, machine learning is kind of the current buzz phrase. If we think of like big data and Internet of Things, those are kind of previous buzz phrases that we still hear a little bit. Machine learning is the current one, and it kind of encompasses all of those computer algorithms that they were talking about in those definitions that are used to make decisions, predictions, or classifications based on data. A little bit of a mouthful, hopefully a good idea. So why do we do machine learning? What's it good for anyway? So we could categorize people or things. We've got good loans and bad loans. We could predict likely outcomes. If we have a machine process where we're trying to produce wafers or whatever, and we want them to have good qualities, we want to take the factor inputs and predict whether or not our wafer is going to be good as it comes out the end of the assembly line. We could also identify maybe previously unknown patterns or relationships. I've got all this data in a database. I can throw it into machine learning and maybe it can tell me that these people are connected and these people are connected. And I didn't know that before. We could even detect anomalous or unexpected behaviors. And I think Chris is going to talk later a little bit about this, where he's going to try and find a rare event sort of detection. And so all of these things are possible with machine learning using different algorithms that were written for different types of tasks. An algorithm that is good for categorizing may not be good for identifying unknown patterns or relationships, and vice versa. So what are the types of machine learning? We've talked about these different categories, the tasks that they can do. They can fall kind of generally into two categories, supervised and unsupervised. So what do we mean by that? With supervised learning, we give the algorithm both the inputs, the things that we want to predict on, and an output, either the classification that the observation had or that final measurement that we took at the end. And then the algorithm determines the relationship between them. It's supervised because we've given them information about what the result is. And examples of supervised learning fall under decision trees, neural networks, random forests, regression, support vector machines, k-nearest neighbors, and Naïve Bayes. So then for unsupervised learning, we give the algorithm the inputs, all of those possible predictors, but we don't have any outputs. We don't have any classes. We don't have a final measurement. And the algorithm then does the work to try and find clusters or other information that might be there. So I mentioned clusters there. Clustering obviously would be an example. Self-organizing maps, which is a type of clustering. We have association analysis, and then singular value decomposition is another method that can be used. We don't have a platform that specifically does that, but JMP uses it in several different routines and pretty prominently in Text Explorer. So you might be surprised that I've listed regression as machine learning. That's also why I can say that we've done machine learning since the very beginning. Most people aren't thinking of regression, though, when they think of machine learning. They're thinking of these really fancy algorithms like the decision trees and the neural nets, etc. But regression is technically machine learning. So with machine learning algorithms, we have a possible trade-off between accuracy and interpretability. Machine learning algorithms, we can walk through, say, the path that the decision tree came up with to make our prediction, but there's no meaning behind those cutoffs. When I go to this particular factor and I split there, there's no reason other than this is where a best predictive value to why that cutoff is there. In support vector machines, the coefficients that are produced have no meaning. They're just used to whatever the outcome is. But these models can produce very high predictive accuracy, which is, obviously what we kind of want. On the other hand, we have interpretability. Regression models provide model coefficients that have an inherently interpretable. So we've all heard, if we've taken any sort of statistics class with regression, our slope coefficient has, this model says if I increase this input by 1 unit, my response will go up 10 units. Very clear, very interpretable. We know what it means. And so in generalized regression in JMP, we have both the lasso and the elastic net methods, which allow for better predictive performance, but still give you an explainable regression model. So it kind of is a combination of this machine learning mindset and explainable regression. Finally, Galit Shmeli talks about this in several of her papers on, she calls it the explain versus predict problem. Are we trying to explain what's going on, or are we trying to predict? Sometimes we're trying to do both. Does that lack of interpretability from these machine learning algorithms matter? Maybe, but it depends on your use case. If the algorithm accurately predicts what you want, gives you those desired outcomes, maybe that's all you care about. If it's predicting what's coming off of your assembly line in a good manner, and that's what you need, then that's fine. However, stakeholders want to have concrete reasons as to how they can, say, improve their score. Say a loan applicant's application was denied and they want to know what they can improve, excuse me, for a future application. We may want to have an explainable model that says, well, you really need to improve, say, your credit score, or your debts need to come down before we can give you a loan. And so we may need that more explainable model. And finally, the key for any model is whether or not you can put that output into action. If I create a model and then it just goes and sits on the shelf and I never do anything with it, why did I spend the time to do that? I want to be able to use that to improve my process, to make those good forecasts, to make the decisions about, am I going to approve this loan, or am I going to issue this person a credit card, etc. So computers win, machine learning, boom, we'll just give it the data. We don't need a human anymore, right? Not so fast. Because there are algorithms. I had that huge slide with all that list. Which one's best for that problem? I feel like this slide is really an advertisement for all the remaining talks in this show today. Mary and Ruth are going to talk more about the different types of models, and Kamal is going to discuss a little bit about which model is best. So there's lots out there. Which data should be included or excluded? If I have a database that I can query to get all my information, do I want to include these fields or those fields, or why or why not? And then Letty's also going to talk about outliers. Should we include or exclude those? And where's the point of diminishing returns? A lot of these models, you can just, particularly like in decision trees, we can just keep splitting and splitting and splitting, and it may improve our predictive accuracy to a point, but I can keep splitting and maybe get a fraction better, but not a lot better. And so is it worth it making this more complex model to not really get that much better performance? There's a great example in the Netflix prize a few years ago. They were trying to predict going to enjoy another movie based on your previous movies, and a team came up with this really great model but it took like 2 hours to run. And I don't know about you, when I'm watching a Netflix movie and I'm ready to start the next one, I don't want to wait 2 hours for it to tell me which one's coming next. I need it right away, or I'm going to go do something else and not stay on Netflix. Finally, are there any inherent biases in the model? Particularly in mortgage lending, there are particular factors that we can't use in making our decision, such as race and gender. And so, but the data that we do provide to the model could be correlated with those factors that we can't use, and kind of and so it could choose a model that on the backside kind of latently is based on those factors that we can't. The computer won't know that. If we go and take a look at it, might be able to see if there is that bias in there. And finally, when should that model be? I created this model, I used that model to change my process to try and improve what's coming off the assembly line. After a while, those parts that are coming off the assembly line don't really match what we used for the data to create the model. And so the model is no longer accurate for what we're producing now. We should maybe take some of that new data, update the model, and see if we can continue to improve, sort of a continuous improvement process. So I have a little bit of time where I can demo some of these platforms. We're going to focus on supervised learning today. And I'm going to look at two machine learning platforms that we've had around in JMP for a little while, but we've done some updating recently, K-nearest neighbors and Naïve Bayes. And then a brand new platform that came in JMP 15 called support vector machines, which we like to not confuse with structural equation modeling, with those very similar acronyms that both came out in JMP 15. And so it did cause some confusion around the JMP halls for a little while. Really enunciate V or the E in the acronym. So with Naïve Bayes, it calculates the probability of a membership in either the good or the bad factor based on the conditional probabilities of the level of the predictors. It's a lot of probability talk, very confusing perhaps. If you like probability and you're interested in Bayes' theorem, it's really fascinating to see how this works. And so I suggest maybe you can go and look at that. One of the issues with the Naïve Bayes is that it makes this strong assumption that predictors are independent. That's not necessarily true, of course. We might have a data set that has predictors that are collinear. If there's the diabetes data set that we have as a sample data in JMP, we have both high cholesterol, low cholesterol, and total cholesterol. They're going to be collinear with each other. And if we use them in this particular platform, we may have some inefficient results because of that collinearity, because they aren't independent. Very quick algorithm, maybe not quite the best results unless you do have that true independence. With K-nearest neighbors, it predicts the responses based on observations that are nearby to it. Those distances are measured by Euclidean distance. So I'm going to look at kind of the people whose characteristics are closest to me, and then decide what the predicted value for me is going to be. If it's a continuous response, it just averages those K-nearest neighbors. If it's categorical, it chooses just the most frequent class that's in those K-nearest neighbors. And then with support vector machines, it's called a maximum margin classifier. And what it's trying to do is minimize the space around that line that separates the classes. So if we look at the graphic, we have the green dots and the red dots, and we're trying to max the space that's between them to get that best separation to make our decisions. The points that fall on those lines become what are known as the support vectors, and why it's called support vectors. And then there's a distance metric similar to the K-nearest neighbors algorithm. There's a linear kernel that uses Euclidean distance, and then a radial basis function kernel that uses a Gaussian measure to determine how similar those points are. And there are parameters involved in that kernel that have to be chosen. And that's a common feature of machine learning algorithms. There are these hyperparameters that we have to tune to try and find our best model. So that's the end of the slides. We're going to hop over here to JMP. I'm just going to use the equity data set that's in the sample data. I really like this data set because it is a pretty good sized set. It's almost 6,000 rows, which is often a feature of machine learning. We're wanting to use big data with it. We're going to try and classify whether it was a good loan or a bad loan based on the various predictors. The other reason I like this data set is because the validation column that's here includes what's known as the test set. So with machine learning models, we always have observations that we're going to train our model on, and we need which is the best model, because remember we have those hyperparameters we're going to be tuning, and we use the validation set to choose which one is the best. And then ultimately, once we've chosen the best, we go to the test set to say, okay, how do we really perform on these observations that we have not used in creating and choosing our model? So that's why I like this data set for these demonstrations. So most of the machine learning, supervised learning platforms live under predictive modeling here. The unsupervised learning, a lot of them are down under clustering. So I'm going to look at Naïve Bayes first. Validation, invalidation, bad is our response. I'm going to use all of the other predictors except the debt to income ratio because it has a lot of missing values, and I don't want to deal with missing values today. So we're going to hit OK on that. Notice that was very quick. We have our results here, but we can see that we have a misclassification rate of about 18% on the training data. Not bad. I would be okay with that under a lot of circumstances, but it's not great, and I wonder if we can do better. Over on the validation side, it's about 19%, pretty similar, so we don't risk overfitting. But that does seem to me that we might have some collinearity in the data because we didn't get as good a misclassification as maybe we should. I could imagine that there probably are some variables that are related to each other. If I went over to the multivariate platform, I might be able to model them and see what those could be. In the interest of time, we'll just move on to k-nearest neighbors. Fit the same model because otherwise, or not the same model, the same predictors, excuse me, because otherwise it wouldn't be fair to compare the models. And then over here we see that it's set to go to about the 10 k-nearest neighbors. Usually 10 to 20 gets a pretty good model. I'm just going to leave it at 10 for today. We hit OK. Notice this takes a little bit longer, but it's still pretty quick. Remember, this is 6,000 rows of data. Boom, there it is. And right away, we have our model selection here, and we can see how that misclassification rate is changing as we increase the number of neighbors that we're using to make our predictions. So in this particular case, actually just looking at the one nearest neighbor, the person who's most similar to me in this loan application, gives me the best predictive value. We can take a look on the training set, about 6% misclassification. And the validation, only slightly higher, about 7%, which is really nice. And then we can scroll down to get a few more details. We can take a look at the confusion matrix for that best model. We can see that it's doing a pretty good job. So it looks like maybe we're classifying a few too many goods. A few too many are being classified. In fact, they're bad, etc. And then we have that also in a mosaic for that visual quick look to see how it's doing. So I'm impressed with the neighbors model. That's really great. Much better than the Naïve Bayes model. And sorry, it just said my internet connection is unstable. I hope you're okay over there. So let's go to support vector machines, see how it can do. We'll fit that same model one more time. Hit OK. And immediately it pops up with some the choices that we have to make. What kernel function do we want to use? The linear kernel, which is just that Euclidean distance. It's very similar in a lot of ways to discriminant analysis. And then the radial basis function, which fits the line but allows that separating line to have curvature. I'm going to go with the radial basis function because a lot of times there isn't just a straight line that splits the data well. We want to allow it to have some flexibility to find, say, this cluster that lives here in the bigger mass of data. I'm going to leave these our hyperparameters, as they're set, the cost parameter determines what the penalty is for misclassifying a point. So if we want to penalize ourselves classifying and make sure that we do a better job of classifying on the front side, we would increase this cost parameter. The gamma parameter affects how much curvature we're allowing into the line, into that classification line. We'll just leave those at the defaults for now. Go ahead and hit go. It'll take just a couple of seconds. There it is. We see our response profile. We can see here, there's that curvature that I talked about. It's not just going through there. Of course, it's really not a line when we have more than two predictors. It's what's known as a hyperplane. So it probably wouldn't be a straight line through two anyway, but we can see that there is that curvature. We can come down and say, well, how did this model perform? And we see in our misclassification rate about 10% on the training, so better than Naïve Bayes, not as good as k-nearest neighbors, but not too bad. But we have those hyperparameters. What can we do? Maybe we can get a better model. I'm going to close that up. I'm going to notice we have this model comparison up here. We're going to return back up to that in a little bit after we fit this next model. I'm just going to go 1.25. So we're going to penalize for a misclassification a little more, allow a little more curvature, and we'll go just a fraction longer. We can see here now we're kind of getting more of a circular area here in the profile plot. So it's limiting more where that good risk category is. If I quick close that, pop up to the model comparison, we can see that we actually did improve. This is now our smallest misclassification rate, training of just under 4%, validation just under, doing a really good job. Still not quite as good as k-nearest neighbors, but a really nice model, I think. I'm going to do one more. There we go. Here we can see again, now that circle is really closing up for that good risk. Pop back to the model comparison. Wow, my training rate is down, misclassification rate's down under 1%. That's really awesome, but it also makes me go, maybe I'm overfitting the data a little bit. I look at the validation misclassification rate. We did still improve there though. We're down to just under 6%. So I like this model. I have a validation misclassification rate that's better than the k-nearest neighbors one. Wow, maybe I'll go with this. But it is a fairly complex model. It took a little bit longer to run. If I were in a hurry and needed to predict quickly, the k-nearest neighbors with just a single neighbor that I have to find might be a faster model and give me essentially the same predictive value. So that's a choice that you would have to make. I do want to point out though, one of the things that I really love about JMP, and this ties into Pete and Mary, is we have the profiler. Yes, the support vector machines and other machine learning platforms are these black box models, but with the prediction profiler, we can actually get an idea of what are the important factors going into this model. So if we take a look at this one, we can see that in the low loan values, we're pretty much guaranteed that this is a good risk loan. We can see then going across that the other factors have a little bit to do with it. So if some of these others got to the higher ends, our risk goes from being good to bad fairly quickly. If your job category is an other, your risk is maybe a little bit, it's a little bit more risky for us to give that loan, but not too bad. It still looks like it's going to be a good choice. However, if we scroll over into that higher category, it really becomes clear that when that loan value that you're applying for is high, you're really just not a good risk no matter what your other categories are. And so at that higher level, it's just all about the loan. If it's a large dollar amount, sorry, really don't think that we can lend you that much. So it's a great way to take a look and see how the factors are impacting the model and the predictions that you get in a quick, easy, intuitive sort of way that a lot of other machine learning platforms out there don't have. So that kind of wraps it up. I didn't really make a decision here. I think I like this model. I like the k-nearest neighbors model too. I guess it would depend on how quick I need to make that decision for my loan applicants. And so we'll talk to the boss and see what they say. So anyway, that kind of wraps it up. I hope you've enjoyed it, and we'll let you back to you, Julian.
Outstanding. Thank you so much, Elizabeth. I'll remind everyone that Elizabeth's recording will be at community.jump.com/jumponair. So if you want to watch it back through to soak up all her knowledge at a little bit slower of a pace even, you definitely can. So thank you so much, Elizabeth. That was great coverage. Our next segment, we have Leedy Trutney here from SAS Analytical Training, and she is going to be taking us through a really important topic, which is exploring outliers in your data. Leedy, welcome to the show.
Thanks, Julian. Let me share my screen. There you go. So this is an example from some of our SAS education training, and it's just a little piece. It's not as complicated as what Elizabeth was talking about, but I'm going to talk about outliers because when you're doing predictive modeling, it's important to know if you have outliers present in your data because it might affect your models that you're going to go get. And so I was laughing watching Elizabeth's presentation because I did the same thing. Okay, so how do you define an outlier? Well, I didn't go to Google. I went to the dictionary, and the dictionary said a person or thing situated or detached from a main body or system. So this is this person who is socially distancing correctly right now because they're detached from all the other group of people. And the second definition was a person or thing that's different from all the other members of a particular group or set. And that's one of those things where you show up wearing the wrong color jersey at the sporting events that you're going, and you really stand out in the crowd because you are with the opponent instead of the home team. And then the last definition is the one that I was most amused by, and it says a data point on a graph or in a set of results that is very much bigger or smaller than the next year's data point. I was like, seriously? That's how descriptive they get on what an outlier is? And so there's got to be a better way than saying very much bigger or smaller because that's not very specific. So how do you determine what is an outlier? Well, what I'm going to talk to you about is there are multiple techniques of determining what is an outlier. And the best one, the favorite one, the one that everybody likes to see is the outlier box plot. It's been around for a long time. It's very visual. It's awesome, right? So just to remind you what are the piece parts on an outlier box plot, it shows up in JMP in the distribution platform. So it's right next to the histogram. And it also shows up in Graph Builder. You can show outlier box plots all the time. But did you know how the outlier box plot is created? Well, that's what this slide is talking about. So the box is defined by the 75th percentile and the 25th percentile. And the tail is drawn out to a point that is called 1.5 IQR from the box. And then any point that is greater than that 1.5 IQR from the box is deemed an outlier. Okay, what's IQR? I have that over here. IQR is that difference between the 75th percentile and the 25th percentile. So this is very visual. It's nice and JMP. I can go and circle and highlight my outliers and then decide what I want to go do with those outliers. And it's a great way of viewing how many outliers do I have in my data set. But the challenge with this is it's awesome, but you have no control over it whatsoever. It is fixed. You can't change it. It is 1.5 times the IQR from the box. So notice what's going on here is 1.5. I'm going to call this my multiplier, and IQR is going to be my percentile. So along, I want to say maybe in JMP 13, might have been in JMP 12, I don't remember, but there was a new platform that came out that was called the Explore Outliers platform. And it's amazing. I love it. So sometimes when you're looking at that outlier box plot, especially in a screening situation, you get too many observations that are deemed outliers. And you want to have more control over what do I want to treat as an outlier. And so there's 4 different techniques in this platform. I'm only going to talk about the first 2, and I'll let you go read more about the multivariate one. So I'm going to describe this quantile range and this robust fit outliers and what they're doing. Okay, so my outlier box plot was deemed by a multiplier times a percentile. So my quantile range is going to do the same kind of thing. Only now I have a choice, and I can change what my quantile is and what my multiplier is. So the default when you open it up is going to be 0.1 for the quantile and 3 for the multiplier. So what it's going to do is figure out what the low threshold is and the high threshold. and any outlier is going to be something that is less than the low or more than the high. So same concept as that outlier box plot, it's just, it's a multiplier times a quantile difference, but you get choice on what the quantile and the multiplier are. So let's see how that works. Let's go through the math on how that works. All right, so this is what it's going to look like in JMP. It's going to report to you what is the 10th quantile and what is the 90th quantile. So for these data, I've got a 970 and a 1035. So I'm going to take the difference between that 970 and 1035, and that answer is 65. This is kind of like my IQR on the outlier box plot. So I've got 65. My multiplier here is going to be 3, so I'm going to multiply that 3 times the 65, and I get a 195. I'm going to take that 195 and I'm going to subtract it from the 970, so I get this 775, which is the low threshold. And I'm going to add it to the 1035, so I get the high threshold, which is 1230. So the table is going to provide to you what is the low threshold and what is the high threshold. And then it's going to count in the whole column how many values are less than the low or more than the high. And in this example that I have on my slide, there are 50 that are less than the low or more than the high. Now in JMP, it will start listing out those 50 so you can see what those numbers are. And then you have some actions that you can take based on that. Okay, so that's how the quantile range outliers work. So we have outlier box plot, and then I have the quantile range outliers. And then I'm going to talk about the robust fit outliers. So these are going to be less sensitive to outliers than non-robust estimates. So there are 3 techniques here. They are called the Huber, the Cauchy, and the quartile. So this is a little bit different. It's not a multiplier times a quantile. It's a multiplier times a spread. And it's how many spread units there are away from the center. Spread units away from the center. Okay, that feels like the normal distribution, right? So if we think about this normal distribution, I think about anything that's more than 3 standard deviations away from the center might be deemed an outlier, right? Well, on my robust fit, I'm going to use 4. Now, we talk about this on the normal probability plot. We talk about the standard deviation in the center, and we know how those are calculated. On these robust fits, I'm using different estimates. I'm not using standard deviation and mean. I'm using different estimates. So Huber is using something called Huber M estimation to estimate the center and the spread. And Cauchy is using the Cauchy distribution to estimate the center and the spread. And quartile is using the median as the center and this number as the spread. So again, you have choice. You get to decide what the multiplier is. They're all going to be multiplier times the spread away from the center, but it's going to decide, and you have choice on what the multiplier is. Okay, so let's go to JMP and do that. So I have this probe subset data table open. So the probe data is in the sample data folder, and it has 387 response columns in here. And I'm going to only talk about 2 response columns. So I have made a subset of this data, and I'm not looking at all of the different columns. So I have 2 columns, and they have unusual things going on with them, which is why I'm going to talk about only those 2. Now, think about it. If I've got 387 columns, right, 387 response columns in the original data, one of the actions that you can take when dealing with outliers is excluding the row. So just hold that thought. I want to think about that. Right now, I've got only 2 columns. So the first thing you always want to do is a distribution of the data. So I have a script saved where I'm doing the distribution. And here's my distribution of the data. I'm going to scoot this over so I can see this side by side. So both of these responses have a fair number of outliers, right? My outlier box plot, I've got some on the low side, I've got some on the high side. I've got a bunch of outliers on both responses. I have about 5,800 rows in the table, so you can tell I have some missing values in both of these columns because it's using only 5795 and 5711. And the other thing I want to point out to you is that the HF peak VA column has the maximum value of 9999. Now, the Explore Outliers utility has a really cool addition to it that's called the highest nines report. And in fact, sometimes, especially with some automated measurement equipment, specifically in electrical test kind of things, when I get a bad reading, it doesn't always say, oh, that's a bad reading. It puts in a 9999. So it would be nice to be able to know how many of those highest 9s we have in my data column. And this Explore Outliers report will do that for you. Now, notice in this, it has to be the absolute highest value. And sometimes you'll get it where, it could have happened, it didn't, but it could have happened on this ICH FEQ, where most of my data is down here in 5 and 6 and less than 10, and then I get a 9.9. Well, if everything else is less than 10 and I get a 9.9, that's probably an unusual value. So it can be 2 9s, it can be 3 9s, it can be 4 9s, it just kind of depends on what the data is. Okay, so let's go explore these outliers and see what's going on. Now, if I were going to look at these outliers right now, I have a lot of outliers. A lot of points are deemed outliers based on this outlier box plot. So the Explore Outliers utility is here under the screening platform or screening submenu. So I'm going to go Analyze and Screening, and then it's the first item here that's Explore Outliers. First item that's Explore Outliers. I have these in a group, so I'm just going to select the group and say Y columns and say OK. And now I'm going to scoot this over to the side so we can see my distributions at the same time. So I'm going to, again, do the first 2. So Quantile range outliers. Okay, so let's look at that. This is the method where it's telling you what the quantile is and what the multiplier is. So the multiplier has a label of Q. This is my multiplier. So the default is 0.1 and the multiplier of 3. I can choose, if I had a long list of columns, I could choose to only show columns that have outliers, which is kind of nice. I can, and these are the actions that I take. So whenever I do this, the first thing you want to do is notice whether or not you have a 9s report, because if you have a 9s report, you want to deal with that first. And I do have a 9s report because I chose this column because it has the 9s report to talk about this. So let's look at this column, HFE peak VA. It says I have 38 rows in the table that are 9999. 38 rows in the table. And if I look up here, it says I have 44 total outliers, and it's listing what those outliers are. And then it says, oh, by the way, you've got 38 of these 9999s. Okay, so what do I do with those 9999s? So my options here, I don't have as many options on the highest 9s report as I do on the outliers report. But when developing this material, I learned something that has been in JMP for a while, but I didn't know about it. And I love it. It's my new favorite thing when dealing with stuff like this. So what it says is select the columns and choose an action. So you actually have to select the column here or nothing's going to happen. So I'm going to select this column here. And let's talk about my 2 choices. I can add highest 9s to missing value codes, or I can change highest 9s to missing. So what are those 2 things going to do? If I change highest 9s to missing, it's going to take those 38 rows in this column, and it's going to just delete those values of the 9999, and they will be gone, and that will be missing in that cell. Okay, so that's one thing. I can't get them back. And then the other thing is the change, add highest 9s to missing value codes. Well, what is missing value codes? Missing value code is a column property that I can add that says, when you encounter that value in that column, treat it as if it were missing. If I look at the cell, it's not the value is going to be in the cell, but it's not going to be used in any analysis because JMP's going to treat it as if it were missing. So that's really protecting your data. It's not removing anything. It's not deleting anything. I like this. I like this as a technique to not delete data because I hate deleting data. It's bad practice to get into deleting data. So I'm going to add highest 9s to missing value code. And JMP's going to respond that says your data in memory has changed and you should consider saving it with a new name. Okay, thank you, JMP, for warning me that I'm saving my data or changing my data. And you're going to look at it and say, well, looks like nothing happened. Something did happen. And so if I look back at my data table and I peek at that column, you'll see I have a column property that's denoted by that asterisk that says there's missing value codes. And so here's what it looks like. It says column values that are to be treated as missing. Okay, cool. 9999. All right, awesome. I have that. But after I do that, I actually really need to hit this rescan button. So I want JMP to notice the fact that those highest 9s are now treated as missing, and I'm not gonna worry about them anymore. So I'm going to hit the rescan button. My highest nines report is going to go away. And my outlier report is going to now say I only have 6 outliers there because those 38 rows that were 9999 are now disappeared or are treated as missing. Okay, so always deal with the highest nines report if you have it first. If you don't have it, don't worry about it. That means you didn't have any highest nines in your data table. That's okay. So now let's talk about how to deal with the rest of this stuff. So what are my options up here? I can select my rows. I can color the cell. That's actually coloring the cell in the data table. Coloring the rows is going to add a color to the row state and color in the every analysis. Exclude the rows is going to remove that row from any calculation. Hiding the row, remember, removes it from any graph. Exclude is going to remove it from calculations. And then I have my friend, the add to missing value codes. I can choose to make these outliers be missing values, or I can flat out change them to missing. So those are interesting options, and you have to be careful on what you're doing. Now let's talk about exclude rows for a minute. Remember, I have 2 columns here. What if I had 100 columns? I'm going to deem something an outlier in 1 column, and it's going to exclude that row for all of the columns. So if depending on how I'm using this data, if I'm trying to use these columns in analysis to build a model, I just have thrown away rows when I use that. So I'm hesitant on the exclude rows depending on what you plan on doing. And the same thing on missing value codes. I could still go do that. I could change to missing. I'm going to put my distribution back up, and let's talk about this next variable, the ICH FEQ. My quantile range outliers is telling me that I have 12 outliers selected there. So I'm going to select those rows, and I can see that they are selected here, and it's only determining these are outliers. So it's not as aggressive as my outlier box plot on determining what is an outlier. And I'm going to choose to color those rows, and so it's going to make them pink. And I think this is interesting. You don't get choice on the color. It's going to be this hot pink color. So, and notice these hot pink outliers on ICHFQ, some of them are also outliers on my HFE peak VA. So some of them are outliers on this. And I'm going to say, oh, wait a minute, but I still have those 9s there. Why do I still have the 9s there? Well, okay, I took an action. I didn't recreate this distribution platform. I didn't recreate. Remember, automatic recalc does not turn on analyze menu. So I'm going to actually just, see it's turned off. I'm going to actually go ahead and redo that analysis so we get, okay, now my highest 9s are gone. But I can still see that I have different number of, I have 12 that are selected down here, and I don't believe I have 12 up here. I can go and check that. I've got 6 that are selected up there. So some of those outliers that are down here, oops, let me select again. Some of those outliers are lower values on the HFE peak VA. Okay, so let's look at the other options. So I'm going to open the gray triangle next to commands and look at this robust fit outliers. And what I want to point out to you is the technique of the quantile range outliers on this one decided there were 12 outliers. And down here on my robust fit, well, Huber decides there's 27. If I look at Cauchy, it decides there's 47. And if I look at Quartile, it decides they're 21. So for this particular variable, these 4 techniques are giving me 4 different answers on how many outliers I have. Now, I'm not even going and changing what my quantile is or my multiplier up here, but I get different techniques on what different answers of the number of outliers based on the technique that I'm doing. And so it depends on which one you have selected. If I select, I'm going to deselect the Cauchy and the Quartile. I want to see what the difference is on this 27 versus this 12. So now I'm going to select rows down here, and I can see that I get some number of outliers that are here on my outlier box plot that the Huber technique is deciding are also outliers. Okay, so that's a little bit confusing. So what should you do, right? What should you do? So that the question becomes, which method should I use? So when I was developing this and looking at it, I'm like, well, I need to read more. I need to study more about this. And so I found SAS actually has an amazing statistical library, surprise, surprise. And there was a book in there. I only chose one book, and it was called the Barnett and Lewis book, Outlier in Statistical Data. It was a very large book, and I did not read all of the book, but there are many reference documents that are all about outliers. So this is a deep subject of the ability to go and find what's going on. So one of the suggestions in the book was what's the distribution that you're using. So you figure out what the distribution is of the data before you go and do that, and use that distribution to help you determine what outlier detection method you should use. Well, JMP can certainly do that. Under analyze distribution, you do continuous fit and fit all, and it will tell you what is the distribution. And you can use that to help you decide which technique to go and use. And then the real question is, what do you go do? Okay, so I determined some things are outliers, and I guess I am hesitant with the thought process. I've had a lot of people in training over the years that they decide this is an outlier, so let's circle them and exclude and hide. And I decide others are outliers, so let's circle them and exclude and hide. And pretty much you're just throwing away data arbitrarily, and I disagree with that approach. Don't do that. That's really, really bad practice. So what I would prefer is the recommendation of investigate the outliers. Just go figure out what happened on them. Why did they occur? What can I learn about them? Sometimes those outliers are excellent things that I want to know more about. I can choose to leave them unaltered. I can adjust the values. So in the Barnett and Lewis, they summarize by saying this: you can welcome the outlier, you can reject the outlier, or you can accommodate the outlier. And I like those three things: welcome, reject, or accommodate. And you got to decide for every outlier that you have, what are you going to go do? And then I've got this option of excluding the row, but again, don't forget that that's going to affect absolutely all variables in that row. So when I go do this on many columns and I randomly or arbitrarily exclude all the rows of all the outliers, I just have excluded a lot of values in my table. Luckily, JMP in the tables panel will tell you how many rows did you totally exclude, which is awesome. I can choose to set the values to missing, and I can add the values to the missing value codes for that column. So there's lots of approaches. We have many different options. You got to think about what is the action that you're going to take and how is that going to affect the analysis that you're doing. So when doing predictive modeling, I need to know if the outliers are there and what actions those outliers are taking and how they're changing my model. They might be changing my model significantly, and I should be concerned about that. So this is an example of something that is like in our training. So Julian, that's back to you.
Outstanding. Thanks so much, Letty. Yeah, that's such an important consideration in all of our model building. And so, yeah, I hope people will look into the SAS education courses. There's some really excellent training for JMP out there. And yeah, I know you all go into a lot more depth than what you're able to share with us today. So thank you again for being on the show. In our next segment, we have Mary and Ruth back for another edition of Which Model Win. This time, they're taking us through predictive models. Mary, Ruth, welcome to the show.
Well, thank you. Oh, I'm practicing my social distancing with my JMP scarf. Sorry. Hey, Ruth. How are you?
Hi, Mary.
So I have the opportunity once again to present with my favorite colleague, Ruth, and we're going to do Which Model Win? And we're going to focus today on predictive modeling. We're trying to get our Zoom coordination here.
Yeah, good start, good start.
Good start. So today, once again, as I said before, we're going to focus on predictive modeling, and we're going to try and use data or that represents housing prices in an area that we'll disclose in a few minutes what we're looking at, and we're trying to predict price. So we have these characteristics which we think are important to run a model with to predict the price. So what does that mean? So, you know, Ruth, I do know that you in another life would love to be a real estate agent.
It's my dream, Mary.
And with your analytic background, we both get to kind of geek out on this data and figure out what the pricing would be for a home in Cincinnati. And you know I've been held up for a while.
Yeah, it's been a tough time for a lot of us stuck at home.
watching Cincinnati WKRP, you know, and so Cincinnati's come up on my radar. So as I said before, we're going to do predictive modeling, and our goal is to build a prediction. And what we want to do is we want to build a predictive modeling and the model's going to give us a price, right? And then once we get that price information, we're going to go out and poll and see what the actual costs were. And so for our example, and what we did, we found out an extra bedroom was extra money. So if we had a price or predicted selling price at $258, that's what our model gave us, and the actual selling price was $255. Woohoo! High five! Our model did pretty well, and so that's what we want to get. We only can do the best of the data with the data that we have, and then look at what's most realistic in the area that we're looking at. So as you could tell, I don't know if you heard my music. I was playing the WKRP theme song. So let's get started. So one of the things that I like to do, and you should always do when you get your data, is kind of clean it up, look at it, and get a sense of what that data is telling you. What's the story? What's in it? And I like to use the column viewer. I like to use distribution, and I use those tools to look for outliers. I use them to look for missing data or levels or categories. And for continuous variables, I like to look at the min, max, and the mean. It gives me an idea of things. So here's an example output from the column viewer from our data that we're looking at. And you can see the lot size, we have a lot of missing values. And as Leedy alluded to before in her prior to this presentation, you know, you have to make a decision about those outliers and what you want to do. So I know I have outliers. I also know for my area, I have 3 levels. And that's important. 3 levels are manageable, but you know, 100 levels may not. So you might want to group variables in a certain way. And I also tell for my continuous data, the minimum home is 50K, which I kind of like. Maybe I could afford that. And the maximum probably is the one I want is 1.65 million, but the mean range is about 250. So I get a sense of the quality of my data and the categorical levels and the number of missing very quickly. And a bonus in JMP 15 is I'm able to get the distributions that I can look at them as part of the data table and take a quick scan across. And what's interesting to me, or what jumps out at me, is city. So you can see city has 120 levels, right? And there's the city, and those are the areas and the townships probably within the city. But that's too many levels to put into a model. So I wouldn't use city, but I would use the area, the 3 levels, because that makes more sense. And of course, we could see the price distribution that's skewed quite a bit, but I think it'll be okay for the models that we're going to run today. And that's the other thing that you look at. You look at the data from using column viewer, distribution and such, and it kind of directs you to the right model or algorithm you want to use to build your models. So now that I have a good sense of my data, I'm cool with it, I know what it's trying to tell me, and I know what I want to tell it, we should probably move on to the next step. And what, if I understand correctly, Ruth, don't we have, we want to kind of guide the model. We want to kind of prevent this overfitting and be able to test the model out. And my understanding is we want to use a validation column.
Yeah, that's exactly right. And Mary, we've looked at this data together before because as your real estate agent, I'm obviously not just putting you on the fly here. When we've talked about it before, you mentioned that you wanted a validation column as the method that you were going to use. So we've got a couple different ways we could test how well we predict, but this is a really good one, especially if you're new to predictive modeling. Using a validation column where you hold the same data in 3 different groups, a training group, a validation group, and a test group, is going to make it super easy at the end to compare all your models to each other. That end comparison happens on that test group. So the test group is this holdout data that we can hold out until the end and do a final comparison for all of our models on the test data. The test data never gets used in making the models at all, so it's a fair comparison at the end. The training data is the big chunk of data that we use to fit the models on. But there's actually a secret middle data set that we sometimes need that we call the validation data that helps us decide when to stop fitting the models on the training data. And so that has to get used in the modeling process, so it's not the true holdout. So I've seen some people who are kind of new to predictive modeling just use a training and a validation set. This only really works when you're trying to decide when to stop building one model. If you want to compare models at the end, you need a third data set, this test data set. So that's how we set up our data, Mary, for your Cincinnati example.
Excellent. Hence the acronym TVT, train, validate, and test.
That's right. Earlier, Mary said to me that she thought that sounded like a disease, and I said, no, I think it's the solution, but that's too nerdy to actually say like genuinely now, so I'm just repeating it. Okay, so the point of having the training, validation, and test set is to get to this model comparison at the end so that on the test data, we can do some kind of comparison of our models. So here you can see in the model comparison, we get to divide it out by the training, how it performed, how the models perform on the training, how they perform on the validation. But those, we don't want to use them for model comparison. Those were for model building. We only want to look at the test data for our actual model comparison. And then we pick one of our possible metrics for comparison, like the R-squared. So R-squared is a measure that you want to be high. High R-squared means you're fitting the whole space really well for your model. So Mary, based on this model comparison output, what would you say is our best model?
I think it's the neural net.
I think you're right. Yeah, by R-squared. That's yeah, exactly.
All right, so we can go to the models and run them under the analyze predictive modeling. And I can see that we have the different models we're going to run, and I think we were going to focus on the tree methods today. And
yeah, that makes sense.
Have the validation column. And then once we run all our models, we have this ability to compare, model comparison. And of course, we have the formula depot at the end if we need to want to share that output with other programs or other things, the scoring code.
Absolutely.
All right, so we know how to navigate there. So let's get started. Ruth.
Exactly. If we try to do those tree methods, that's the partition tree method, the boosted tree, and the bootstrap forest. I'm going to throw in the neural network also because, as you saw from our final model comparison, it's actually going to perform really well in this case. So for all of these, as we set them up, we're going to be looking for price as the response, and we're going to be looking for these 6 factors. You can have a mix of continuous and categorical factors, but remember that data cleaning stuff that we want to deal with missing data. So if we've got a lot of missing data, figure out what to do with that. There's a lot of options in JMP's predictive modeling, but we're not going to talk about those right now, but just know the missing data is a big deal. And also fewest categories possible for something categorical. So that's why we chose this area with just 3 categories instead of something like the location or city that had 100 and something. And then we have a spot to put that validation column, and then JMP is going to know what to do to fit the model on the training and then test it on the validation, and then we'll also be able to see how it fits on the test. So here's our first model, our first simple tree. So partition is a simple tree. It's a classification tree if you're predicting classifications, and it's a regression tree if you're predicting something continuous like price. So we've got a regression tree. And this split history tells you the story of what happened when you were fitting this partition. So the R-squared is plotted on the y-axis here. And the point that's got this big line at 15 splits, that's where JMP is telling us, let's stop building the model at 15 splits. So the summary up here tells us 15 splits here. We see the training R-squared and validation and test R-squared. Those are the R-squareds at 15 splits. So if we read across to the y-axis. So the blue line here is the training data. And as we split, every time we make another split in this partition and another split and another split, on the training data, we're just going to get better and better and better in the R-squared because we can explain more and more and more of the training data. The problem is at some point we're really overfitting to that specific training data. So that's why we want to look at the validation data, which is in red. We're going to totally ignore the orange test data. Totally ignore it. It's plotted here for us. That's great, but we're saving that till the very end for the final model comparison. So we're just focusing on the red validation data. And here we can see for a while the R-squared was increasing, but at 15 splits, that's when it levels off and then even decreases a little bit at some point. So what happens in JMP, His jump follows this out for a bunch of splits, and when for 10 splits it wasn't improving on the validation R-squared, then it peels it back. And that's where it tells us we should stop building this model at this point.
Oh, now that's great. I love a picture, so I think that having the split history, the visual with the numbers is a good representation of the information.
Yeah, exactly. And it tells you what jump did in the background. It went out all the way to 25 splits, and
Right.
then it peeled it back. Yeah.
And we're not overfitting.
Exactly. So then for that partition, another thing we can get is the column contributions, which gives us the summary of how important these factors were in the model. So we can see square footage explains a ton of the variation in price. It's 64% portion. Baths also explains a bunch, almost 30%. Year built explains about 5%. Area, almost 2%. Bedrooms never comes into this model, and lot size never comes into this model. So we just get those first 4 factors in our model.
Why do you think that?
Well, when we see the boosted tree and bootstrap forest, we'll see more things show up. What happened here probably is that there's probably a correlation between some of these things. So obviously, you put more bedrooms and bathrooms in a home, the square footage probably goes up. Definitely bedrooms and bathrooms are correlated. So if you've got 5 bedrooms, you're more likely to have more bathrooms also. And when 2 things are correlated in a partition, it's going to pick the one of those that seems to explain the most. And then there's not a lot of additional information from the other one, so it just never shows up in the model. So it looks like bathrooms is telling us more than bedrooms is in this case. So Mary, tell me about your dream home.
Well, it looks like $169K I could afford. 3 bedrooms, 2 baths, 2,100 square feet. Well, I'm only living in less, just doubled my square footage from living in the city. And I only have 1.5 baths and, 2 bedrooms. I can afford this. This is awesome.
According to our prediction, you can afford this, but I'm going to warn you now, some of our other models are going to get a bit of a different estimated price here. So this is why it really matters for us to pick a good model. Don't just believe the model you want to believe. So, so here for this example, yeah, you like this one, but I don't know if I think you're going to be disappointed when we go to the contract for this home. We might find that our predicted price didn't perform that well compared to the actual price. So here's a second profiler for a second version of a home. So everything's identical except I added a bathroom in this home, and look at that massive jump in price. So this model is, it's an interesting model. So just 1 extra bathroom for this home. So it's a 3 bedroom, 3 bath, 2,100 square footage home now. Huge jump in price. Something I think that's really interesting is if you look at that bottom profiler at the square footage part.
Oh yeah, it has a little bleep.
Exactly. Yeah. So I think, Mary, if we just add some square footage to your home, we can actually reduce the price, the predicted price.
I like it.
Yeah,
Another
you can
closet.
see, yeah, exactly. If we add a closet, you're actually going to get a better deal. So you can see that the partition type of model actually allows you all kinds of funky shapes. You don't have to just have constantly increasing or constantly decreasing. You can fit really complicated shapes. And unlike with regression, where if you thought it went up and then it goes back down, you have to think ahead to put a quadratic term in your model. Here, it just pops out at you. So if this is what the data is suggesting, this is what happens in your model. So,
is this why tree methods are good?
Yeah, absolutely. They're really good for this nonlinear relationship, or you just don't know if it's linear or not, or what it is. But the weakness for the one tree method, just a simple partition, is that it might just choose one of the factors from correlated factors. So in this case, we never saw bedrooms come into the model.
Yeah, because bathroom was the enforcer.
Exactly, the muscle. So how do we fix that? One option is we can boost the tree. We can make a boosted tree. So we start with our original partition, and then all the information we weren't able to explain, we build another tree on that to see if we can get more prediction from that. And then we build another tree on those residuals and another tree on those residuals. So a boosted tree starts with the original tree and then adds layers of information on top of it. Or a bootstrap forest. Oh, you're right, exactly. Yeah, crowdsourcing, where you start with your information and then you add other people's on top of it.
Yeah, a layering.
Exactly. You're such a young person, Mary.
I am, I'm young at
with your crowdsourcing. You whippersnapper. So bootstrap forest is our other option. A bootstrap forest is going to make a whole forest of trees. But if we just ran the partition over and over and over to make a bunch of trees and we don't change anything between them, we're going to get the identical tree every time. So what we have to do is introduce some randomness, we randomize in two ways. We randomize the columns. So sometimes bedrooms and bathrooms will be in the model. Sometimes only bedrooms will be in the model. Sometimes only bathrooms allowed to be in the model. We also randomize the rows. So those two aspects of randomness allow us to get different trees, and then we're sort of averaging them together. So here's some output from that boosted tree.
Oh, wow.
Yeah, if you remember our R-squareds, we'll see a summary table later, but this improved a little bit over the original partition. But also look at the column contributions. We've got area coming into play now. Bedrooms is still out of the picture. And for our predicted price for that dream home of yours, the 3-bedroom, 2-bath, it's not 170 anymore. It's now 202.
It's going up.
It's going up, girl. And then the bootstrap forest.
Hopefully you're a good negotiator.
I mean, I better be. I'm going to be great at this real estate job, Mary. I just know it. Okay, so the bootstrap forest, also a slight even higher price. So now we're up to $208,000 for that home. Notice that bedrooms actually popped into the model from the column contributions. Yeah,
and the R-square is pretty good too.
Yeah, it is. This is our best model so far. And bedrooms is able to come into the model because we didn't start with just one tree where we committed to that bullying tree where bathrooms was edging out bedrooms. We actually got a lot of different possibilities.
Randomizing.
Yeah, exactly.
Randomization.
So here's just those column contributions between the simple partition tree, boosting that tree, and then the bootstrap forest. Is there anything notable here to you, Mary?
Yeah, it looks like with the bootstrap forest, we got almost all of the characteristics that we wanted to use in our prediction is actually there. We have square footage, baths, year built, lot size, area, and beds. So they all got to come and play in the playground.
Mm-hmm. Yeah, that's definitely true. And it might be the case that we want fewer terms to be in our model, but if our goal is the best prediction, and our R-squared was better for bootstrap forest, that's suggesting that having all the terms in the model actually was kind of helpful in this case. We had better predictions. One more model I'd like to throw in, Mary, if you don't mind, is the neural network. We said we do tree-based methods, but I just think this one performs very well very often.
Now, isn't neural network, I heard people refer to it as like a black box, or this model that things happen, something goes in and then something comes out and we don't know what happens in the middle?
Yeah, and this is something Elizabeth said on her talk a little bit earlier today as well, that a lot of these like support vector machines and neural networks and these types of models that are very complicated in the background, they are hard to understand. There's an equation in the background that's just a massive equation with all these different slopes that all interact with each other. And so it's really difficult to interpret what's happening. However, as Elizabeth pointed out, looking at the prediction profiler can really be a great tool to make it feel less like a black box. We can actually see from the prediction profiler what's going on back there. So those crazy equations allow us to have a very unusual shape if that's what the data is pushing us towards. So just like we with partition and with tree-based methods, we're able to find dips and rises and falls and things throughout the space. We can do that even more flexibly with the neural network.
I noticed with the neural network, the profiler, the curves are smoother. They're not steppy.
That's a really good point, because the tree-based methods are binning things. They're saying if you're between this number of bathrooms and this number of bathrooms, you get the same price for everything in that region. And then even when we boost or bootstrap, we still are averaging sort of those trees together. But the neural network is actually fitting smooth curves to each other. And yeah, we see the smooth shapes.
That makes sense.
Okay, so we're back to this.
Am I going to have another test?
Let me think of a new question. Oh, yeah. How about for the other fit statistics, RASE and AAE? What would we want? How would we decide the best model if we used either of those fit statistics?
Well, those are your error terms from the model, and I believe that we want them to be lower. So we always want the R-square high, and we want the error terms to be lower. And that will give us a good idea of a good model. Yeah,
that's exactly right. So in this case, we get the same best model no matter which of those three fit statistics we look at. The highest R-squared was the neural on the test. The lowest RASE is the neural, and the lowest AAE is also the neural. So by any of those metrics, we get the same answer in this case, that the neural across the whole space of all of the predictions, the neural network seemed to be fitting the best to that whole space.
Ruth, would you ever have a situation where the error was larger or not in balance like that?
Sure.
You know,
Yeah, I think that's
I was
possible.
just curious.
Yeah, and so you're going to have to decide what metric is more important to you. Do you want to be explaining the overall variability in the R squared form, or do you care more about the error? Or sometimes you might actually only care about part of the prediction space. So maybe you don't really care about year built in the 1800s. You only care about homes that were built 1900 or later. So you're not so much worried about how well it fit back there. So making those kind of exclusions in the model to begin with would be really helpful. Yeah, there's a lot of nuance to this.
Yeah, a little witchcraft and magic, right?
Definitely witchcraft and magic.
And I see with the profilers, that will kind of help us determine that prediction space, and we can figure out what's important.
That's exactly right. So if you want to do a really good job predicting in a certain region more than the rest, you can use the prediction profiler to help you kind of hone in on that, see what those predicted values are, compare them to actuals that you have in your data set. So see how well you're performing just in that subspace. This can be a nice tool to help you with that. So here's our hypothetical home again, this 2,100 square foot, 3-bedroom, 2-bath home. It's in the city. It's not rural or suburban. It's got 20,000 square footage lot size, and it was built in 1965, same home. Here's our 4 different predicted prices for the original partition tree, about 170,000, all the way down to the neural network at 270,000. So there's quite a broad spread for this particular home. There's a lot of variability in our possible predicted values depending on what model we choose here.
Well, I want to choose the one that gives me the cheapest price.
I know you do, but that doesn't mean it's the best model. And you might be horribly surprised when we go to sign the contract that they're asking for a much higher price than we predicted.
I see. So as we move and change the values, like for bath, 2 baths, my dream home would be 4 bathrooms, 3 bedrooms, and probably about 3,000 square feet. I'm probably out of my price league, right?
I'm guessing you are. That makes a lot of sense. Yeah, so we can wiggle around in this space and kind of explore it. We can see how the different shapes perform differently. So you can see the partition is just a step function, really simple, one tree, just each range of those steps is one predicted value for everybody in that whole range. The boosted tree is adding some tree on top of the step function, so little step functions on top of step functions. The bootstrap forest is averaging a bunch of step functions together, so it gets even more lumpy. And then the neural network has that smooth, lots of different kinds of curves that are attached to each other. So you can kind of see how they perform differently, how they're able to do slightly different things because of the nature of the type of models that they are.
Now, when I look at the neural net and I see that dip around 1860s, should that be something that guides me and says maybe I want an older home?
It might be.
I probably have to put in a new bathroom.
Yeah, I mean, you might need to put in a bathroom. I'm just guessing. So yeah, absolutely. At this point, we want to explore the space and think about what really is the subspace that we're most interested in and kind of look at performance in that region specifically.
And would you ever use the profiler to dictate your model, or is it just more to help you interpret and put in the what ifs? If Mary changed her mind and said she wanted 1 bedroom, 1 bath, and 900 square feet versus 2 bedrooms, 3 bathrooms and stuff.
Well, I think it's really helpful for exploring what you're describing right now, kind of just the exploration, but it is also, you can actually print out, like you can ask to save the columns in the data set for all these predictions. If you wanted to enter new hypothetical homes and you had 100 new homes you wanted to predict at the same time, you could add them to the data table instead to do that prediction.
Excellent, excellent.
Well, thanks everybody.
I'm excited to go shopping. All right.
I can't wait to help you pick out this home. We're going to put our masks and our gloves on. We're going to, I don't know how I'm getting to Cincinnati, but it's going to be a fun adventure for us.
Well, let's get I'm into RVs. I've been watching the RV channel for a while, so like buy your RV. So I'm waiting for a road trip.
Sounds great.
Well, today, Ruth and I shared with you our approach to creating and building models, and what I'd like to sort of summarize was the data prep step is really, really important. Understanding your data, making decisions about how you categorize them or group them, understanding if you want to deal with outliers or missing values and how you want to do that. Based on that interpretation, you're going to pick the algorithm that best fits the data once you decide what you're going to use. And part of that's accomplished by creating that assessment, that validation column, that train, validate, and test, because we want to train your model, validate it, use that validation to stop that overfitting, and then test that independent data set to see how well the data is doing. And then run different types of models. I mean, we started here with the tree method and the neural net, but there's, as you could see from the predictive modeling selection dropdown, there are other models that you could run, and it might say you've learned something here. You might say, I want to try these other ones. So it's an iterative process to go through, because at the end you want the best model, and that's we weren't able to show them all. Maybe we'll do another session, do a tutorial on all the models. Who knows? And then we're able to compare them. And there's different ways we can compare them. We can do the model comparison, looking at R-squared, looking at the error terms, making the decision based on those values, and also looking at the partition, the prediction profiler, and putting in different values and doing what if. And I know when Ruth starts her career as a realtor, that partition's going to be, smoke's going to be coming out of that mouse as she moves it around and shows her client, you really want this? Like Mary, you really want 3 bedrooms, 3 baths, and 2,100 square feet? I know you. Your budget is below that. So thank you for joining Ruth and I again for another Which Model When. We find these a lot of fun and putting them together, and we hope that you find value in the way that we think about picking which model when. Ruth?
Yep, thank you. Back to you, Julian.
Julian?
Thanks so much, Mary and Ruth. I look forward to your show where the two of you are on a road trip together. Please film that and share it with us, because we can't wait to have that as an ongoing feature.
Have my social distancing scarf.
I can't wait. Can't wait. Thanks again for being on the show.
Thank you, Julian. And bye.
Bye. Our next speaker is Kamal Offlis, who's going to take us through a quick start to predictive models, tips and tricks to build models quickly. Kamal, welcome to the show.
Thanks, Julian. I'll share my screen just a second. I'm hoping everyone can see my screen. Julian, can you see that?
Looking great.
All right. So welcome, everyone. In this session, I'll talk about tips and tricks. It's always a challenging topic because somebody's tips or trick might not be relevant to anyone else. And a lot of times it might come as a little bit listed topics. I'm listing this and that. So what I'll try to do is I'll try to keep it coherent from beginning of analysis stage all the way through the end. And whatever I miss along the way, you can always find it if you by typing on your browser community.jump.com. That's where you'll find a lot of our JMP users or different analysts and trying to look at their data. They come across some problems or they figured out how to solve it. So community.jump.com will be a good source of information if you're looking for any other tips and tricks using JMP or any type of analysis. So from the previous presenters, if you've been following all along, some common themes showed up. When we're looking at our data, there are some missing values. There are some outliers. And we're trying to identify what type of modeling will be more applicable to building our predictive models. So I have like four different sections I want to go through in the next 20-25 minutes. One will start with visualizing our data to understand what's in the data set. So before we go into building very complicated algorithms and then use a profiler to look at the results, what I want to do, take a step back and visualize what's in the data set to make sure that the data we're looking at is the data we expect it to be. And then we'll move on to, once we visualize our data and understand what's in there, to go through some steps of cleaning up our data so that our modeling will be smooth. And then when we build our models, we'll be looking at relevant data at the end. And I'll walk through very quickly, because previous presenters already walked through different modeling options, what's available, and talk about which one to choose and some kind of pitfalls along the way, trying to avoid traps that might come on our way. And then I'll also talk about on which models to choose, not only just looking at the model comparison, but also what to do with the models that once we build them. And then, of course, I will leave you back at the community.jump.com where you can learn more about tips and tricks. So let's start with visualizing our data, and then why are we doing it? So I have this data set, and if you look at the data, I will just look at some summary statistics. There are about 13 different data sets, and they have exactly the same means and standard deviations for X and Y. Now I can look at this statistically from my distribution, and I see for each of those data sets, I have very similar summary statistics. Just by looking at the numbers, it's not really going to tell me what's in this data set. Because of that, what I want to do is I want to visualize to see if that's what I'm looking for. Maybe there's something hidden in the data set I might not have noticed by just looking at the numbers. So what I did is I just took that and put on the graph builder, which is under visualization. Under graph option, there's a graph builder, the very first option. So each of my data sets, I'm looking at them one at a time to see if there is anything interesting. It looks like there's a circle, there's scattered plots, different lines. Now for this data set, maybe clustering will be a better type of solution. For this type of data set, maybe grouping decision trees will perform better. But I can just go through these to have an idea before building a model. So there's a star, or I can just say, go through a triangle, have this animate through it, and quickly go through all 13 sets of data to tell me if there's anything hidden here. So I'll just watch it to see if there's something hidden. You might have seen this data set before, but wait till you get to the very last point, which will be a very surprising result. Any type of modeling tools will probably not going to be applicable because we're looking at a dinosaur of data. So it's always helpful to visualize what's going on in this data. It's kind of like, interesting way of looking at it. And if you've done this type of work, you will also understand that this will drive your results in a very opposite direction than what you want to do. So I have a very statistical example of that. You might have seen this. It's called Anscombe's quartet. Very similar to what we walked through before. I'll just turn these up. I have 4 different data sets with exactly the same statistics. And it looks like a simple regression line gives me about 67% R square, explains about 67% of the variation that will be applicable to all this data. And I started the session saying that we need to visualize our data to understand what's happening before we go into sophisticated tools. So let's look at the data set very quickly. Go to a triangle, turn to show points, and it looks like this makes sense to build a regression line. And I'm using regression as a representative of my model. And of course, there are a whole bunch of different modeling options, but it will, at the end of the day, will depend on the data. Well, for example, how about this data set? If I show these points, and you see, I have a big outlier here, although it's giving me the same result. And scroll down, how about this one? I show the points here. There's definitely curvature. I probably want to fit a polynomial model. My regression is not going to work for me. And this very particular one is extremely interesting. All my data points are in one location, and the rest one is far away. So if I were to throw all my data into a very smart algorithm, have it run through and give me the results, if I hadn't seen these data points, I could have believed this linear regression would explain everything else. And previous presenters, they also went through dealing with the outliers. I want to show you the impact of removing outlier from the model. So in this case, let me just one more thing here, make sure automatic calculation is on. So what happens, just pay attention to our equation for the linear fit. It's 3 plus 0.5 times x. So if I take my outlier, right click, and remove it from my data set, now look what happens to my linear regression line. And I can do the same here. Take my particular row, right click, remove that data point. I did not use automatic recalculation here. I'll have to go back and rerun it. Just go one more thing here. make sure this is turned on. And if I remove this data point, now my equation looks totally different. So it's important to not only look at the data statistically, but also look at our visual understanding, our subject matter expertise to decide which outliers to remove, which outliers is not. And of course, if you have a lot of variables, the better method will be to go to analyze screening, like Liddy showed earlier, under explore outliers, throw in all your columns in, and then from that, it will lead you to removing outliers statistically, which I will get to that in a second. So that's the very first thing before you do any type of modeling or analysis with the machine learning tools is to visualize our data. So now let's look at an industrial example of where these outliers and missing values come into play. And then what we'll also do is we'll figure out how to screen our predictors and responses so that instead of throwing all the variables into the model, we can understand what's important, what's not. So I'll open this particular data set. All the data I'm using available on the sample data library. So if you want to look at it again later on, you can use it. So in this particular data set, so all data set, they're looking to see if there is any banding on the paper, on the press, by using about 32 different variables that they collected information about. So what I want to do is, before I go build a model, I want to screen for outliers because we visually verified having outliers in our data is going to give you results that are not appropriate for what we're trying to model. Under Analyze, Screening, Explore Outliers, and I'll put all my predictors in, and it will complain. It requires only numeric values, so you can run the distribution on the background and say, okay, now we're back to Explore Outliers. Liddy mentioned about the Quantile and robust fit outliers. These do outlier detection on the individual variable level. However, the ones on the bottom, basically what they do is they look at the correlation structure among your variables and then use that correlation structure to identify where is the robust center of the means and then mark those as regular and the ones on the tails as outliers. And the k nearest neighbors, instead of building one circle of concentration, it will build k many different circles and identify if any of the data points do not fit in that level. And like Liddy said, we have a lot of information about this topic. If you have any questions, we can always help you with that. After the outliers, next thing becomes important is the missing values. Again, our previous presenters talked about the missing values and how they could contribute, what you can do with that. What I want to show you here is under Analyze Screening section, Explore Missing Values. And what I will do is I will start with just the numeric values here, show you what's available, select a few of those and say, okay. Now there's an option here for validation too. I'll come back to it in a second. Once I say, okay, I have a whole bunch of different options that I can deal with missing values. The first three is to give me a report, what's missing in my data. And the next three is basically what can I do with those missing values. And the easiest one, simplest one to do is use a normal imputation. We'll take our data and then use least squares prediction to basically impute the missing values. Now, as your data becomes big, if you have wide data, then SVD becomes faster because since you will have sparsity on your data set, SVD will work faster and better to get there. And finally, there's automated data imputation. What this will do is it will build interactive models between your variables and automatically impute data from the other variables and the existing data structure from that. So if you have missing data in your data sets and you're trying to build a model, you're restricted to just throw away those rows or throw away those columns. Now you can make sense of data and build models accordingly with that. Just keep in mind that the data you will create by imputing is not going to be real, but it will give you an understanding what the underlying process is. So I will leave it at that. And like our previous presenter showed again, if you go to Analyze on the Fit Model platform, where you'll find all your regression tools. Under predictive modeling, you'll find machine learning tools, where you'll have the tree-based methods, neural networks, and other models available. When we first started doing machine learning, and we understand that we want to use our data to build a model, and we want to validate it, like Mary's trying to buy a house, having an expectation what the cost should be to validate our model. And then we want to go out to real estate listing and see if what we predict is actually applicable to real world. So that's our test set. If I were to build a model and put my response, put all my predictors here, I have an option for validation. If I do not select anything and just say validation, if I do not have a validation column, JMP will ask me, do you want to create a validation column? And if I say yes, by default, it will select, okay, how do you want to do that? As a rule of thumb, we use 70% for training, 70% for validation, almost 30% for validation. But if you have enough data, it's more advised to do. Maybe you want to use 60% for training, 20% for validation, and 20% for testing. Now, JMP create a new column for me, and if I just go say run, it will build the results, and it on the very bottom, if I go to the all the way to the bottom, it will not give me on these results, but it will give me basically the details of my model. How good does it fit for my training data, for my validation data, and test data? In this case, it doesn't perform well at all. But we're going to get to the better model by trying different modeling tools, but what's important here is saving training, validation, and test. Now, we're talking about tips and tricks. This type of validation might not be applicable for every data set. If I go back to Analyze, go to Screening, go to Specialized Modeling and Screening, there are different ways that I can deal with it. Under predictive modeling, there is a make validation column option. It will ask you if you want to stratify by certain values. Because when you're building a model, you want to make sure that you want every group to be represented accordingly. You want to group your variables. And most importantly, if you're looking at time series data, you can use a cut point to test your validation. Say I want to use my first 100 rows to train the data, next 50 rows to validate it, and next 50 rows to test it. What I did previously, when I selected validation, it randomly put them in order. So there is no there's no pattern into this. So if you're building a model and if you expect there's a pattern in your data, make sure your validation is set up accordingly. So that's another tip that hopefully that will be helpful to you. Another one that you might have noticed when I went to Analyze, Fit Model, just run through this recall and run it, I get a list of all the variables and they're put in a rank order. Which one is more important than the others? And you will have access to this on all regression platforms. But just putting them all in here and trying to figure out which one is more important than the other becomes a judgment call. JMP provides you this blue line of statistical significance. You can say, okay, the most important one was unit number. I don't think that's true, but you also get a list of every other variable here. There's a quicker way to deal with this. And again, that's under Analyze, Screening. There is an option for predictor screening. In the predictor screening, it will ask me, what is the response you're trying to model? So I'll take my response, and then I'll put all my predictors here. And all I have to say next is okay. What will happen is it will go through each and every one of those variables. And it will run random forest on the background and tell me which factors are more important than the other. So when I'm building a model, and I can comfortably say, okay, these top 8 factors that are more important, I'll just keep those. Copy the column, go back to my fit model platform. If I go to my predictors, you notice they're selected, put them as a list, put my response, and then run the model. Now it will give me a better result. So that's one way to go through a lot of variables at once and then decide what's important than the other. So what I will do next is I was going to talk about different modeling options available where you have access to regression trees, regression-based models, tree-based models, and neural networks. Kind of like I'm running out of my time. I want to show you something very important that I come across a lot working with customers in a lot of different fields. For example, I'll go to my analyze and fit model here, put my yield as a response. This is one of the more important things our customers need to trying to model. Work with a lot of scientists and engineers. What they build, the model they build needs to be reproducible and reusable, and of course need to be explainable to anyone else who is going to use it. And for the purpose, we select, okay, regression platform. It's easy to use. Ruth and Mary talked about it, so we can visualize it and things make sense to us. So what I will do is I'll take all the variables that I think could be important, put them into my model effects. Now throw in my validation as well. And by default, JMP will set the least squares regression. I'll do a minimal report, clean, and say run. I have a model. I'll just say, okay, let's get rid of these guys because, they're not necessarily very significant. I'll remove this, get rid of all those. Now I have a cleaner model, that's fine. My R-square is 53%. Just another tip, trying to figure out which model to use. You get two different summaries, that's summary of fit explanation in JMP. One is the R-square, one is the adjusted R-square. By definition, if we add more factors and try to fine-tune our model, we're going to get a better explanation, right? Because we're going to memorize every single detail in our data set. But as we add more factors, we're going to add more complexity to our model. The difference between R-square and R-square adjusted, one way to see that is the complexity I'm adding to the model worth it? What I'm trying to, if I build a model and R-square and R-square adjusted are very far from each other, so if I undo this, for example, what I did, go back. My R-square was 96%, adjusted was about 79%, kind of tells me that this model will bring in a lot of points of failure that will be very hard to control. So it's important to make sure that you're looking for building models that are squares close to each other. So let me promise I'm going to finish in time. So let me remove some of these factors, clean this up. And then I want to turn on the profiler, which we talked about earlier. That's a very helpful tool that we can use. Let me make so we can see it. Now, linear regression is nice. It's easy to build. It's easy to understand. I can see the relationships. And what I will do, what Ruth did, I'll go to a triangle, optimize, turn on my decidability, and go to a triangle, and have JMP use this formula in the background and tell me what's the best solution for this. I say maximize and remember. So the best case scenario for my yield to be as high as possible, I need my SA to be 80%, pH 2.9, basically all our settings. And if I do that, I can expect my yield to be 154%. If any of you done any type of industrial work, 154% yield is better than awesome. It's better than perfect. It's life-changing. It's like a perpetual motion machine. We can't have that. So that's where the subject matter expertise come into play, what I call as human in the loop. Before you build your data, look at your data to understand what you're looking to do. Because regression models assume your data is normally distributed. So if I go back to my analysis and distribution, look at my yield is pretty good. On average, it's about 96%. But these outliers that I kept in the model, It's pushing my standard deviation, which is about 9%. Without doing any type of analysis, I will expect to have yield values greater than 100% if I assume there's normal distribution. Another way to deal with this, of course, would be I can go to my analyze, predictive modeling, maybe just use the partition platform, do the same thing, put my yield and all my factors and run it accordingly. This will not give me my yield values greater than 100%, and it will also give me a map to the best or the worst case scenario. That being said, this kind of takes me end of my time. I have a lot more to talk about, but like I said earlier, if you have any questions, please let me know. I'd love to talk about these items. And of course, recommend you go to community.jump.com, where you'll find a lot more tips and tricks to deal with the data issues that you might have or you might have come across before. And this is you, Julian.
Fantastic. Thank you so much, Kamal. And I'll remind everyone, community.jump.com/jumponair. And that's where you can interact with Kamal's segment. We'll ask him to put his journal up there as well, so you can also take a look at what he was showing. Thanks again, Kamal. In our final segment of the day, we're really excited to have Chris Gottwald here, Director of Statistical Research and Development, and really the man behind a lot of the routines you'll find in JMP for predictive modeling. And so he's going to take us through machine learning modeling tips. Chris, welcome to the show.
All right, hello everybody. So it's a tough act to follow all the previous speakers here today. So I'm also doing a machine learning modeling tips seminar here, and there's a lot of overlap with what people have already said. And so I will, I think that there's still value in hearing the same kind of message be told different ways and seeing different approaches to solving the same problem. One thing that's true about machine learning and modeling in general is that there's not always one right answer, and seeing a bunch of strategies that people try is, I think, really helpful. So I'm going to give an overview of classical modeling versus machine learning modeling. Then I'm going to talk about how to read patterns in diagnostic plots. I'm going to go over some data preparation steps that are similar to some things that Kamal has shown and Ruth has shown and Elizabeth has shown. And then at the end, I'm going to do an analysis. I'm going to show you my workflow that I use to do machine learning. And I'm going to show a little trick that I found is very effective for handling rare event classification problems. So if you think about statistical models, you can place them onto a kind of a spectrum. This is very similar to some ideas by Galit Shmueli, where you have, on the one hand, models that have a high amount of interpretive value. These are the things that come from first principles models like differential equations. Structural equation models are like this. Generalized linear mixed models are like this also. These are models where we're really trying to reveal some truth about reality. And on the other hand, we have the machine learning models, which have a very predictive orientation and require a less subject matter expertise generally than the interpretive models. So the kind of comparing these, so the interpretive models require a lot of very careful checking to make sure that the data were acquired the right way. You have to know how it was designed or how it was created. When you're going through the analysis, there's a lot of assumptions that you would need to validate, like normality and lack of serial correlation amongst residuals and so forth. And this is because we're trying to set everything up in such a way that we can do inferences, like hypothesis tests, to really get at this fundamental science of what's going on in a particular situation. These models are, when things go wrong with the data, when you have outliers and missing values, a lot of care has to be taken in how you approach them, because everything is about making sure that we have type 1 error rates that are controlled and we're maintaining our power. On the other hand, the predictive models, the machine learning models, they are designed to quickly give you accurate predictions and classifications. As such, these are very accurate models. and they have the benefit of fewer assumptions are required to use them, but this comes at a cost of conclusions that you draw from them aren't going to be as strong as you would had you had a carefully designed study and a first principles model applied to them that was easily understandable. Another big difference between machine learning and classical methods is that you can build your outlier and missing value handling approaches into the study and into the model itself. And this is very easy and very common across all the different models that are in JMP. Now, there's been tremendous success with machine learning. We've seen driverless cars. We've seen AI algorithms beat world champion chess players and Go players. It seems like magic, but it's good to take a step back and remember that machine learning is not a panacea for all kinds of problems with data. So for one thing, machine learning models, like all models, don't automatically allow you to infer causal relations. Causal relations are a property not of the model or of the data. It's a property of how you designed that data. If you changed X and then watched how Y happens, then you can infer a causal relation. If you just observe a bunch of X's and you use some X's to predict a Y, your ability to make causal statements is not going to be quite as strong. Also, machine learning models won't fix your poorly designed experimental data. So if you're a consultant and someone comes to you with a messy one factor at a time study they did, neural networks aren't going to fix that for you. Machine learning models can be risky to extrapolate with. So this is, whenever you're starting to try to predict at points that are different from the distribution that was used to train the data, they can be pretty risky. I think Kamal just showed us some issues with that. And this extrapolation issue happens both directly in terms of trying to predict new points, but also if the population that you model from can change from under your feet, and the model will no longer be applicable. So they have a lifetime. So if you fit a machine learning model in a manufacturing environment and you had a set of tools that you used, the manufacturing tools that were used to generate that data, if a year later those tools are older and the model might not be true anymore for them, they've degraded. Or if you get a new set of tools, it's also not necessarily true that you can apply the same model to the new data from those tools. And also, if you change the measurement system, that also can mean that it's time to update your machine learning models. So in my experience, these are the tools that have been the most successful for me. When looking at prediction performance only, boosted tree, boosted neural, and support vector machines seem to do the best in prediction. If you want to understand which variables are important predictors, however, Bootstrap Forest and generalized regression with the lasso and the elastic net are both outstanding tools for that. And partition models are the most interpretable, especially with small trees. And I'm going to show later on how to combine the accurate predictions from a boosted neural and a partition model to lead to an easier to understand way of making use of that machine learning model. So here's the important question. What is a good machine learning model? And the answer is a model that's going to predict accurately on new data given the kind of information that you're going to have at that time. And to identify that, we build in this performance on new data into our model selection process by partitioning the data into training, validation, and also test sets. So we tune the model on the training set. So this is where we estimate our regression coefficients. The validation subset of the data is used to adjust the tuning parameters of the model. This happens behind the scenes, usually inside of the JMP platforms. And then a test set is used to make a final assessment of the best model that you're going to use. And for doing this partitioning process, we have tools that make this really easy. So once we've done that partitioning, we fit models, and they're going to give us fit statistics like R-squares, likelihoods, RASEs, RMSEs, Gini indices, misclassification rates, and those are good to consider, but I think the best way to go is to look at diagnostic plots as a guide for finding a good model. So my favorite plots are different between continuous responses and categorical responses. For continuous responses, I love actual by predicted plots, where we're plotting the actual values on the y-axis and our predictions on the x-axis. We want our predictions to be correlated with our responses. And so if they're exactly equal to one another, then our model is perfectly accurate. And this is what the actual by predicted plot would look like. Now, if you see this in practice, it's probably too good to be true, and you should probably think about why that's happening. The worst case scenario is when the predictions are independent, or the actual values are independent of the predictions. And that's what this is over here. This is where you have an actual by predicted plot that looks like random scatter. This is a model that is no better than guessing. A mean model is the simplest model possible. It has, for any value of x, there's only one and only one predicted value. So our actual by predicted plot has the range of the data on the x-axis is 0, and we have the complete range of the responses on the y-axis. And as we're going through the modeling process, we're going to start with simple models often, or especially the JMP platforms will start with simple models and add complexity to them as they're going. So you'll end up with intermediary steps that look like this, where the range of our predictions is shorter than the range of our response. This is a sign that, as far as the modeling process goes, you're probably not done yet, and you need to either add complexity to your model or find more predictors in order to find a model that's going to be lined up more nicely along that 45-degree line. It's great to look at these plots on the training set and the validation set side by side. In the early stages of modeling, you'll often see stuff like this, where they both look like sticks. When you've gone too far, this is the signature of that. This is when you've made your model too complicated and you've got overfit. We have tight points along the 45-degree line on the training set, but now our predictions are independent of our response actual values on the training set, and we're just getting random scatter. So this is too complicated a model for this data. The best model is the one that does well on both of these. I call that the Goldilocks model, that's not too simple or too complicated. And we should see a similar pattern on both of these two plots along the 45-degree line. A lot of the time, the validation plot will be sparser than the training plot because there's usually less points in the training set. So this is a good goal, is to get to a situation that looks a little bit like this. I will say too that when you're modeling, if you see patterns, like if things are deteriorating over here, or you've got a weird cluster of points that are fitting poorly, you can use the interactivity in JMP to highlight those points, go back to the data table, and then look at what x's those points corresponded to identify where what kind of situations are problematic for this particular model. When I have a categorical response, I like ROC curves the best. They are easy to use, but describing them is a little bit abstract. So like a good ROC, so this is where we have a binary classification. We're predicting a response level of yes. And a good ROC curve has area under the curve of 1, or the best possible perfect fit situation has an area under the curve of 1, so it would go up quickly and over to the right. Unlike a actual by predicted plot, when you have an ROC curve that hugs the 45-degree line, that's a bad scenario where your predictive model is no better than guessing. And if you're over here, you're actually way better guessing than using that model. It's very severely overfit. So the way that these things are drawn is we fit a probability model in JMP. For each of our rows, we have a probability of the outcome of interest. We sort those from high to low, like this. And when we're drawing this plot, every time we get the response that we're modeling, we go up a point, we go up a level. And every time we guess the other category, we go to the right. So here, the sorted probabilities for this model go from 0.663 to 0.559. And we have, drawing the plot here, we have a yes, then a yes, a no, a yes, a no, a yes, and a no. So that's how they're constructed, but it's a little bit easier to just use them to in a similar way to actual biopredicted plots. So this is what an overfit situation looks like. On the training set, the plot goes all the way up to 1 and then over to the right. And then on the validation set, you'll see a substantially different plot. This is a situation where you're going to want to go back and probably remove some variables or use a simpler model. Here's a situation where we've got, looks like there's some significant terms on the training set, but when we actually apply it to new data, we're actually below the 45-degree line here for a lot of the way across the plot, which means that this is not a good model yet. And here's a Goldilocks plot where we see the same general pattern in both training and validation, going up and then over to the right without going perfectly into the corner. And generally speaking, the validation plot is kind of choppier than the training one because we have fewer observations in them. So now I'm going to go into a demo where I'm going to illustrate these ideas. So this is the diabetes data set. It's a sample data file that I've modified to insert missing values into it so I can show you how I would work missing value handling into the modeling process. We have 9 demographic measurements on patients that were taken at one point, and then a year later, there's a column that indicates whether or not their diabetes disease had grown severe over the course of that last year. So we want to use these variables to predict this outcome. And this is a rare outcome, so we're going to use some tricks to come up with an effective classifier based on our machine learning model. So the first thing we do once we have our data organized and we have the data table that we're going to use for modeling, I go to the Make Validation Column utility that's under the Predictive Modeling menu in JMP Pro. From there, you can either just click through and you'll get a random allocation of rows to training, test, and validation. I almost never use that though. I always stratify by my response. So here it's severe. I want to make sure that the ratio of yeses in my training set is the same as the ones that are in my validation set. So when I add that, the cut point column option disappears because we don't offer that a combination of cut points and stratification. Cut points are used when you are going to do a time series prediction model where you're predicting into the future. So it doesn't make sense to chop up your data into random subsets. You want the time series to stop at a certain point on time, have training in the early rows, and validation and test in the later rows. And then if you have grouping columns, that's kind of like a machine learning blocking type situation. So if you want all the data from a particular tool in your manufacturing process to be together in the training set or the validation set, you use this option, and it's available when you're using stratification as well. So we get in, I tend to use 2/3 training, 1/3 validation usually. So the defaults here are 3/4 training, 1/4 validation. So there's a nice trick that you can use so you don't have to enter all those decimal places, where you can enter a whole number into the training set, say 2, and then 1 in the validation set, and you press scale, and it converts that 2-to-1 ratio into corresponding proportions for you automatically. And then the next thing I'll do is I switch to the formula validation column type, just because I like to change the validation set sometimes and look at different models that are fit to different subsets of the data. Once we click go, then we have a validation column that's been added to the data, and we're going to supply this to all of the modeling platforms that we use after this. Now, what this has done is it's made sure that the proportions of the response are the same in both training and validation. This is very important when you have an extremely rare event, you don't want to end up in a situation where the training set gets all of the rare events and none of them are in the validation set. So this makes sure that that can't happen. If you have a continuous column, then it does something pretty smart to ensure that the distribution of that response is as identical as possible in the training and validation sets. So the way that it does that is it sorts the response, identifies the ratios of training and validation, and randomly allocates, say in this 2/3, 1/3 situation, 1 run into validation and 2 into training for the top 3 values of the response. And then we'll go to the next 3 values of the response, randomly allocate 1 of those to training and to the validation set, others to training, and so on and so forth, going through the entire range of the data. And so through this mechanism, we obtain a very strict control over the distribution of the response in those 2 data set, in those 2 partitions of the data. Then the next thing I would do is go into explore missing values. We supply our continuous columns with missing values into them and the validation column as well. I will point out that in version 16, we're getting a lot better at this, at exploring missing values. And in the next release of JMP Pro, we're going to allow combinations of categorical and continuous variables for imputation in this platform. What I would do is use automated data imputation. It does a machine learning algorithm that finds a low rank approximation to the data and then uses that to regress the missing values using the non-missing ones in a dynamic way. It's really pretty slick. And we do that. It found that a 2-dimensional principal components type model was the best using the validation set. And it then creates formula columns that do the imputation wherever it was needed. So it kind of fills in the holes for us. And these are formulas so that if we have new rows that are coming in that we merge to the data set, it'll automatically give us those. Predictions of our missing values. So I'm going to go use the neural platform to do this model. I'm going to supply it my severity indicator as my response, and all my imputed columns as X's. I'm going to use the same validation set. Boosted neural networks are really very successful in modeling, and so what I would do is set a small single layer Tanch neural network as my base model that I'm going to build from, and I'll use up to 1,000 boosting iterations. I'll never get there, but because it's going to use early stopping to decide when it's going to finish adding nodes to the neural network. And I press go. It's going to fit a 2-layered a neural network to the model, and then calculate the residuals, fit another one, and do this iteratively. And if you're adding single layer neural networks to one another, then that total sum is also a neural network. And so this is why this boosting neural option is like a stepwise procedure for neural networks. So we've got our measures of fit here. We see that it's done 17 boosting iterations before it was no longer able to improve the model on validation. And it's led to a 34 node total neural network that has this architecture. My ROC curves are looking pretty good on training and validation. So this is kind of a happy story here. This is looking good. I will point out that although this is a black box model, the profiler is an excellent tool for understanding what's going on between the inputs and the outputs. And we have this great option for assessing variable importance that does a simulation that will tell us which variables are the important ones in this model, and we reorder the profiler so that the most important variables appear to the left. So we're kind of front loading the visualization for you. So the most important variables are what you see first. Now, we're not doing so well with this model at predicting our response category of interest. So we have, whenever we had an actual severe case, or when we had actual severe cases, we were most of the time predicting no, that they weren't severe. And this is because this confusion matrix is using a 0.5 threshold to make that call. And so what is a better practice, in my opinion, is to use the partition platform to identify the threshold for us that will be optimal for this model in this data. So I'll save my prediction formulas back to the table. So I have them here now. Here's my probability of yes. And this is the most likely severe using that 0.5 cutoff, which I never use this column that gets saved out. Now we're going to go into the partition platform, and what we're going to do is we're going to use the same response category as our Y, but instead of using the X's, I'm going to use the probability prediction formula from the neural network as my X, and I'm going to use the same validation set. So when we get in there, I'll split, and now it's found that a cutoff of 0.17 on the probability. So if your probability of a severe diabetes progression is less than 17% or 18%, you almost certainly don't have it. Or it's not going to be a severe case. If it's greater than that, then the odds are pretty close to 50-50 that you have a severe case. So you might want to test people who have a probability of severe that's greater than 18%. We could go a little bit further and try to come up with a yes, no, maybe system. So if it's less than 41%, we're still probably okay. But certainly whenever that probability is greater than 41%, we probably have a case of severe diabetes progression. So this is like a green light, yellow light, red light type system that we've very quickly come to for this problem. So we've compared machine learning models to classical statistical models. We've learned how to use diagnostic plots, and in particular how to read different common patterns in them so that you know when you have a good model or when you need to work some more or when you've gone too far. We've gone through the machine learning modeling process on a rare event classification problem, going through the steps of setting up the validation column, treating missing value imputation as part of the modeling process itself, fitting boosted neural networks is a quick way to find good models, and use the partition trick to solve our rare event classification problem. And that's all I have for you today. Thank you very much for the opportunity to speak today.
Outstanding. Thank you so much, Chris. Just a reminder to everyone that we'll have Chris's materials, as well as everyone that was on the show today, at community.jump.com/jumponair. That's also where you can interact with our speakers, ask questions, get any of the materials, or just watch their segments again. Lots and lots of great tips and information was shared in today's episode, as I'm sure you saw. So I know I'll want to go back through and watch those again. Be sure to follow us on all of our different social media channels. We do share often, and we have a lot to share. Make sure you join us next week. Remember, we're off Monday for Memorial Day here in the United States, but we're on Wednesday and Friday. And remember, it is our last week of the Jump On Air first season, so be sure to join us for our final shows. Until Wednesday, we hope you stay safe. We hope you stay healthy. We hope you're staying close, even as you're keeping your distance. Have a great weekend, everyone. Take care.